Hello, everybody. Can you hear me?
Yes.
Okay, thank you. All right. Give it another few seconds and I'll get started. I'm recording the session. All right, so it's 10 o'clock. We'll get started. I must admit, I was hoping for a few more people today, but hopefully people will be watching the recording of this as well. But I think that coming to the Zoom sessions is going to be more valuable than watching the recordings, just overall. I'm going to download one of these pen and paper tests just to give you a little bit of context for the kinds of questions that you'll be asked. Obviously, they're not going to be asked in exactly the same way on your real test, which I will be going through questions like that as well. But I thought what I would do today is give you a little bit of context for the kind of stuff you'll be seeing. Let's see. So we're going to do fall 2018. So I'll download the key here as well. Okay. And I just wanted to go over what kind of things you would be seeing. If anybody has any questions or anything, feel free to chime in at any time. All right. So I'm just going to open this test here, fall 2018. You have access to it as well. All right, I know I'm going to have to share my desktop here, so I'll go ahead and do that. Okay, so you should be able to see my screen. Is that correct? Can I get an answer, please?
Yes.
Thank you. Thank you. All right, so the questions we're going to be talking about today will be questions 1, question 2, and question 5. This one over here. Okay. So question 1, this is with direct relationship to the lab as well. This is one of the things you'll have to do in the lab is figure out the reaction order. So I'm hoping that, you know, before you come to these kinds of Zoom meetings that I'm having here, it's good to have watched the videos, the ones that I put in the syllabus for the specific Zoom meeting, to make sure you have at least a little bit of a background as to what's going on. I'm not going to explain things from scratch here, but I will give you a little bit of minimal background to try kind of get your head in the right place. At least that's my idea here, and to then give you some context for the kinds of questions that will be on the test that you'll be taking. So we've got our rate law here. This will determine how fast the reaction goes, and it's going to be rate equals Ka, which is this one here, and that's to the power of m, and B, that's to the power of n. And your mission here in this kind of question is to find m, n, and k. So you need to find these powers here, and the k as well as the overall order of the reaction here. So for this kind of question, what you'll do is you've got 3 experiments here, and to find the order with respect to m, what you're going to have to do is find 2 reactions where the B ends up cancelling out. And you can see that here, if we chose reactions 1 and 2 here, you can see the 0.652s are going to be the same. Now, the reason for this is because you can see here that in order to find this value for m, we're going to have to put experiment 1 and experiment 2 together. In this case, we're going to do experiment 2 over experiment 1, so that the values for the experiments here for the B values will end up cancelling. And you can see that if we do that, and the reason we do experiment 2 over experiment 1 is because we're looking at the rates here, and we can see that if we put this one over this one's bigger. So that's why we choose to put it on top. But in the end, what we're trying to do is compare these two experiments by looking at the one that cancels out so that we can end up having something here. So we do that, and you can see if we take 0.00216, divide it by this, we'll end up getting 26.15. Now, really, in reality, this student shouldn't have put this units here. Those units should have cancelled, and it would have been 26.15 equals 5.00 to the m. And you can see here, it's almost like 25. So 25 is equal to 5 to the m. So it should be clear that m is 2. You can also get the value of m by using this kind of log arrangement here. Take the log of this divided by the log of the 5.00. That'll give you the value for m. That's how you can solve for a power. Or you can just eyeball and say 25 equals 5.00 to the power of 2. And that will give you the m value. Does anybody have any questions so far? Anything so far? Okay, just want to get the thing here. All right. So I still have your attention? Can I have just one signal, please?
Yeah, we're here.
Thank you.
I did have one small question. You said you can just eyeball it.
Yes.
Eyeball what? The 26 and the 5?
Yeah, that's right. And you can do a little bit of trial and error. You can say, because you know it's going to be a whole number.
Okay.
So you can say to yourself, well, if 25 is 5 to the power of what? And you can say 5 to the power of 1. Nope.
Oh, got you. Okay.
5 to the power of 2. Yep.
Okay.
Certainly not 5 to the power of 3.
Okay.
So you don't have to do this whole math thing here, but it it can be helpful if you're not sure.
Mm-hmm.
I'm just going to digress here just a little bit, and I'm just going to pull up my paintbrush here. Now, if you had a situation where it was 8 equals 2 to the n, and you wanted to solve for n, I'm hoping that nobody would say that n was 4. What you could do is you could do 2 to the 1, nope. 2 to the 2, nope. 2 to the 3, yes. Remember that 2 to the n is 2 times 2 times 2, n times. And if you do that, then you can pretty easily figure out what the power is. So that's just a little bit more information for that. All right. So you can see that if we're doing the n value, we need to find two a values that are the same. That's why we would use experiments 3 and 1 here. And you can see that it doesn't matter if we do experiment 1 over experiment 3 or experiment 3 over experiment 1. These are the same values. So when they end up being divided, they come out to 1, and anything to the power of 0 is 1. So n is going to be 0 for this one here. Any questions about that, about m and n here?
And m and n don't get any units, correct?
They don't, because they're the orders with respect to those specific compounds. And when we get to talking about question 5, the one that has all the talk about mechanisms and things, you'll see exactly what effect the order has on something. It tells you how many molecules are involved in the slow step. And we'll add more context to that in a little bit. But no, there's no units. The next thing we need to do is calculate K. Now, in order to do that, we can use any one of these experiments, experiment 1, experiment 2, or experiment 3. And it's just plug and chug. So if we're doing experiment 1, which I think is what this student's done over here, you put in the initial rate for the rate. You put A, which is going to be the 0.2, the power of m, which is going to be squared. And then you've got 0.652, and that's to the power of 0. Remember, we're just applying this rate law here and just plugging in everything we already have. The only thing we don't have here is K. Everything else we actually have. So that means we can solve for it. Now, solving for K numerically is not really a big deal. It would just be this divided by whatever you get over here as the result once you multiply everything together. And we come up here with the K value being 0.00216. The units here, that can be a little bit challenging. So I'm going to go ahead and show you how to get those units. And in this instance, what I'll do is I'll try and I'll shorten things out a little bit. I'll just look at the units themselves. So we've got molar per hour over here for the initial rate, and you can see that up here. It's under initial rate on the table. That gives you the units, and that equals K, and the unit with the 2 is going to be m squared, and then we'll have m to the 0. Now, as I talked about before, anything to the power of 0 is going to be 1. So that gets shortened down then to molar per hour equals K m squared. Now, I'm just looking at the units here. I'm not looking at the numbers. So what we can do to isolate K then, and to get the units, it's going to be molar per hour over m squared, like that. Now we can simplify that because we know this rule here. There's 2 rules that I'm going to talk about here. So a to the x times a to the y equals a to the x plus y. We know that rule. That's effectively what we're doing here. It was 2 plus 0 is 0. The other rule we have for powers is this one. And that is when you've got a to the x over a to the y, then that equals a to the x minus y. So you've got 1 here minus 2, which means it's effectively m to the negative 1, h to the negative 1. The reason I'm saying h to the negative 1 is because it's on the bottom. And any time that happens, we can do that. The other way of expressing that is 1 over mh. That'll work as well. And you can see that there 1 minus 2 is negative 1, so the m ends up on the bottom. So that's how we can get the units. I want to point out here, the unit for K is going to change depending upon what the orders are for m and n. It's not always going to be 1 over mh. It could be anything. In this case, it is 1 over mh, but it doesn't have to be that. Does anybody have any questions?
That was helpful.
Okay. Was it more about the units at the end that that was concerning you? Okay.
Yes.
All right. Yes. What I'd like to do now that I've gone through an actual problem that shows all the different elements sort of all put together, I'd like to go through the practice test here and show you how these questions are going to look in that particular context. Now, I want to point out here with the practice test, and I'm going to be opening here this ungraded copy of test 1, that there's videos for every last one of these problems. They're all present here. So you can always look at these just to give you an idea of what I'm expecting or what I'm looking for when answering these questions, so that you can see what I mean by the wording, because that's what usually trips people up, is the wording. So that's the reason I have those there. Let's take a look at ungraded copy of test 1. We'll look at the preview, and I'm just going to go through the first questions that relate specifically to that question. And here we have it. So we've got question 1, question 2, 3, and 4. So these questions are really just the same thing as what we just did, just spread over 4 different questions. So you can see for question 1, we're looking for the order with respect to A. So the assumption there So the assumption there for that one is that we're dealing with a rate equation that looks like this. Rate equals K, A to the M, B to the N. And what you're focusing on here is the order with respect to A, which is going to be the M value. Now, in order to find that, what you would do is you'd want to find two experiments for B that were the same. So you would use probably experiments 1 and 2 here. My thought would be to use the experiment 2 over experiment 1. So it would look like this. You do 792 divided by 302. You know that the K's are going to cancel. We'll have A to be, whoops, the A here, which is going to be 0.160 to the M. And then we've got the...
I'm sorry, Professor. Which problem are you on?
Number 1.
Okay.
I'm sorry. I think I did make a mistake here. Let's go back a bit. Here we go. 792. Yeah, it's going to be 0.867. Yeah, we're looking at question 1 here. 0.867 to the M, 0.199 to the N. And then we'll have... Now, you see, I'm doing experiment 2 over experiment 1.
So the rate on the bottom would be 159, not 302.
Would it? Yeah, you're right. I'm sorry.
That's okay.
Okay.
We know you're just trying to keep us sharp.
Yeah, that's right. That's what it all comes down to. Yeah, I knew what I was doing all along. All right. Yeah, so yeah, 159. Thank you. Now the unit on that is molar per hour, and you can see that those units will end up cancelling. And let's see, so it's K, I'm trying to make this right, 0.160 to the M, and then again 0.199 to the N. And you see that all cancels there. The K's cancel, and then you'll be able to solve that. Now for this one, you will have to use the log thing. I'll go ahead and do that. I don't have my calculator here. Does anybody have a calculator? They can tell me the result of that.
Yeah, give me a sec.
792 divided by 159 is 4.981.
Okay. Don't worry about sig figs here because the M value isn't going to have any units or sig figs.
Okay.
And that equals?
5.38.
Okay. I think it's pretty clear what M is going to be here. It's going to be pretty close to 1, but we can verify that by doing M equals log of 4.981 divided by log of 5.38. Now you can use logs or natural logs as long as you use the same thing. And then that M value is going to come out to something that's pretty close to 1. And that's what you'd put in as your answer. And it even says there round to the nearest whole number. So that's what you'll do. Does anybody have any questions about question 1 there? So question 2 is very similar. And in that case, you would want to be able to find the order with respect to B. And you can see you'd have to use then experiments 1 and 3 in order to make the A's cancel. So you'd be left with B, and you'll do that in a similar way. And I would do 3 over 1 because 3 is bigger than 1 on the initial rate. And that will hopefully give you something that you can work with there as well. I wouldn't expect these to give results that are particularly close to whole numbers a lot of the time. That's not the way these are set up. But you can just go ahead and round to the nearest whole number. It's pretty much what you do in the lab as well, because you never end up getting perfect results there either. All right, does anybody have any questions about question 1 or 2? Okay, question 3. You can see this is where we're solving for K, and I give you the values of M and N as 2 and 3, and here I'm only interested in the actual numerical value for K, not the unit. In question 4, I ask a specific question about how to get a unit, but for this one, you're just looking for K, and let's go ahead and delete all that. So to set that up, you can see it's going to be rate equals K A to the M, B to the N, and then we can substitute all the information that we have here. The rate being 113 K, and then A, which is 0.166 on the molarity. Not worry too much about the units here. I'm just putting them in for kicks. And that's to the power of 3. And then that's times 0.165. And that's to the power of 2. So you can see here that in order to calculate that K value, you'd have to do 0.166 to the power of 3 times 0.165 to the power of 2. Does anybody believe that they'd have a problem doing that on their calculator? Well, on the calculator, actually, I should say on the calculator that you'll be using on the test.
Can you actually explain to me, like, what you did to the exponents from 3 to 2?
Okay, in the problem, it tells you that M is 2. M is 3. Sorry, M is. Oh, sorry. I was looking at the wrong problem. That is not.
It's all good.
Yeah, it actually isn't. But you know. Sorry, I'll have to read more carefully here.
It's all good.
Well, it's a danger, you know. It's a danger. All right, so let's do 2 and 3. Yeah. Because M is, according to the problem, M is 2 and N is 3. And I've just substituted those values in.
So with respect to the powers, you're just saying we're going to need to square 1.6 or 0.166, square the M, and then cube the 165 and the M.
Yeah, but don't worry about the units for question 3. You know, just be more concerned about the numerical value, because that's all I'm asking for in question 3.
Okay.
Now the other, sorry,
I do have one question that's sort of related. It was on the practice extra credit quiz, where we were given not just one line of the table, but we were given the full table and told to find K. So very similar to this question. How do you know which line to pick? Because
it doesn't matter. The K is a rate constant, so it should be the same for every line.
It should be the same.
Or it should be, if it's not the same, it'll be pretty similar.
And if, for example, you've been given a table, a full table, and it asks you to find the rate of K, but you still don't know the M and the N,
you can't.
You're going to have to find both of those first before you can find the rate. Is that correct?
Yeah, you'll do that in the lab, actually. And you'll see the K values you get will be pretty similar.
Okay. Then my math must be wrong, because I wasn't getting similar things, but I think I wasn't doing the powers correctly. So,
all right, just a trick here that I can give you, a tip. If you've got 0.166 squared, that's the same as saying 0.166 times 0.166. And if you've got 0.165 cubed, that's the same as saying 0.165 times 0.165 times 0.165. So if it helps, don't even worry about the powers. Just multiply them by themselves that many times and multiply them by each other and come up with a value that goes on the K side there and divide that into 113 on the other side, and that'll give you the proper numerical value.
Okay.
All right. Any questions about number 3?
Yeah, do you have the answer by any chance? Because I solved it out and I want to check if that's...
Okay. Well, I don't have it. I don't have it here because I'd have to submit it to get the answer.
Okay.
So if somebody wants to come up with an answer, that'd be great, and you can check it. So we'll see. So I'm looking for somebody to confirm the answer once they come up with it. I think we've got 8 people in the room at least, so somebody should have a calculator.
I have a really big number.
Yeah, it's okay. What'd you get?
I have 912, 762.
912. Yeah, that seems to
912,000. 912,000.
Oh, okay. So did you get that?
Yeah, that's what I got too.
Okay. Yeah, so if we're looking at significant figures for that, I'd take it down to 3 and I'd make it 913,000.
And that would be based on the initial rate, or will they all have 3?
Yeah, they'll have 3, yeah.
Okay.
Yeah. So in fact, that's what I would do. And the thing is that the tolerance, I've got enough tolerance on these answers that you know it should account for any significant figure foibles that might occur. Now, if you find that you've got an answer that's close but it's marked it wrong, please send me an email and I'll look at it. I might need to increase the tolerance.
Okay.
But yeah, go on.
Are you recording this session by chance?
I am.
All right, awesome. Thank you.
And I will put up the link.
Yeah, I'm about to go to the doctor soon, so
Okay.
thank you. Thank you.
Yeah, no problem. Okay, any other questions about question 3? All right, so question 4 is the one about the units, and this is the one where, this one is often one people have a lot of trouble with, but it's actually not as bad as it seems. It really is one of those sheep in wolf clothing. It's kind of like a sheep dressed up in a wolf costume, but you take off the costume and all you see is a little sheep. So let's take a look at how you might do something like this one. It says here, so I'll go ahead and we'll do out the rate equation here. Rate equals K, rate equals K. And it's going to be A to the M, B to the N. So it'll be A to the 3 and B to the 1. That's the information we're given because we're told what the values of M and N are. The other thing we're told here are the units, and the units for the rate are going to be molar per hour. The units on A and B, of course, are going to be molar, so it's going to be molar cubed and molar to the 1. Now, what I was saying earlier is that when you multiply two things like this together, molar cubed and molar to the 1, then what you'll have is molar to the 4th. All right, so 3 plus 1 is 4. That's how I get the 4 there. That's that A to the X times A to the Y equals A to the X plus Y, what I was talking about earlier. Any questions so far for that? All right, it's good.
No.
All right, let's take a look at then how we finish that up. So it'll be K equals M per hour over M to the 4th. And you can see here that it would be effectively 1 over hours M to the 3, or M to the negative 3, H to the negative 1. So you could express it sort of either way there. Now, the way I'm getting the 3 on the bottom is it's 1 minus 4 is 3. But since it's going to be negative 3, it'll be 1 over M cubed. Or you could just make it M to the negative 3. Either way. So the question here is asking what the value of X is. And I'm hoping you can see that it would be negative 3. Not 3, negative 3. In the context of that question.
And what part of the question told you that A would be in just molar? Is just that because that's what you're doing and it's experimental, or?
No, but well, I mean, you can see it on the other questions that A is always in molar, B is always in molar, but it's and you can see how it's in square brackets. That means it's a concentration, and I think you can assume that the concentration is molarity.
Oh, I thought the square brackets were mathematical. Okay.
Oh, no, they mean concentration of.
Okay. Concentration of, and so that's going to be molarity every time.
Every time, yeah.
All right, so that's how you need to put the molarity in for the A and the B.
Yeah, the other clue is in the question says the unit of K is found to be M to the X, H to the negative 1. It really couldn't be anything but molar, especially given that the rate was molar per hour as well.
Okay, I was thinking that, but I wasn't sure which way you were supposed to use it. All right, that helps.
Okay. Any other questions about question 4? Nobody should be getting that wrong. Nobody. Honestly. Yeah. Yeah, that's a tough one. But I often find people get it wrong, but there's no real need. It's actually not as scary as all that. Okay, any questions? Any questions at all about that? Okay, well then we'll move on. So question 2 here. And what we're given is a situation where it's just one reactant going to products. And the data here is different to the kind of data we were given in the previous problem. But since we only have one reactant, then we can use a different kind of data set. We can just use the time and the concentration. Now, if you take a look at the actual data that we're looking at, it's actually not really that hard to interpret just on its face. We're starting out with a time of 0, and you can see that the concentration at that time is 0.09980. As time goes on, you'll notice something happens to the concentration. It goes down. Why does it go down? Well, it's because it's reacting. It's really that simple. So time goes up and the reactant concentration goes down because it's turning into products. So what we're trying to do here is use this data here to figure out, well, what's going on? Is it going to be A to the 1, A to the 0, A to the 2? Those are the only real possibilities that we talk about for this specific kind of problem. And the approach we take is to do these 3 lines here where we have A, we have natural log of A, and we have 1 over A for each of these. Now, you might be wondering, well, how do you know to do log of A, natural log of A, and 1 over A here? Well, if you go to the problem, you can see in question 2, with the problem, I give you this table, and it's an integrated rate law table is what it is. And the way this works out is you've got this rate law, and I'm not going to go into the math here, but you can do this. This rate is really kind of like a derivative. And then if you integrate it, you end up with this form of an equation that looks like a straight line. And it goes like this. It goes y equals mx plus b. So that's y. T is x. And you can see that y would be the concentration of A here. And at least for 0 order. And then you've got the time, which is in days, and that's going to be your x value, which means that the slope is negative k and the y-intercept would be A0. So that's just an integration of the rate law, and I don't really want to go into how we get that. But my point is this: the y value in this case is A for 0 order. You can see it's natural log of A for 1st order, and you can see it's 1 over A for 2nd order. And that's what you'll be looking to. You'll be looking to this table, which obviously you have access to on the test because it's right there. You can also see what the slope is going to be in each case: negative k, and positive k. And the y-intercepts we really won't be using. But what's important are the y values: A, lateral log of A, 1 over A. So that's how we know that we need log of A and 1 over A here. Now, to get the natural log of A, you can see that all we do is plug these into the calculator and hit the log button. And that's how we get those. The 1 over A, 1 divided by that, 1 divided by that, 1 divided by that, 1 divided by that. Any questions about natural log of A and 1 over A and how we're getting them? Now, the idea in this problem is that in order to determine whether it's 0 1st or 2nd order, and I told you these integrated rate laws are straight lines, we're looking for curves or straight lines, and the one that gives a straight line is going to be the one that is going to be the order. So what I mean by that is we've got 3 graphs then, and I'm just going to give you an example here of what those graphs might look like. Then I'm going to show you how we actually would do it, or at least I'm going to go through it on here. So for the first one, that'll have a negative slope on it. And let me see what we're going to get here, and I'll just, yeah, 2nd order, okay. So for the first one, you'll get a curve that looks like this. And you'll notice that curve has a negative slope. So that would be for A on the y-axis and time in days on the x-axis. So that's what that one's going to look like if we were going to do that graph. The other one is also going to look like a curve, and that would be natural log of A on the y-axis, and again time in days on the x-axis. And that's for 0, that's for first, and this is for second order, and this will be 1 over A, and it's going to look like this. So that one is actually going to be a straight line. Now we don't actually have to draw these graphs. We can do another thing to see if it's a curve or a straight line, and that is by comparing the slopes between different points on the graph. So in the 0 order, my recommendation, now it doesn't matter which points really that you compare or sets of points, but my recommendation is compare the first two and the last two. Now I know in the mini lectures I think I say to do the first and second and first and fourth or something like that. It doesn't really matter, but if you're going to do something where you're looking to see if it's a curve, the greatest difference or apparent difference will be between the first and second and the third and fourth when we're talking about the slopes. So to get the slopes, it's going to be delta y over delta x in each case. So the change in y over the change in x. And you can see that that's what the student's done here for each of these. Now I'm just going to look at this and see what they did as far as points go. It looks as though they did the first and second and the last and second last. Yeah, it's just like I just did here. But you might not see it done that way all the time. It doesn't really matter which points or sets of points you compare, but the whole point is to come up and see if you get different slopes. And by doing that, you can say, well, that must be a curve. But when you come up with slopes that are pretty similar, and you might be asking, well, just how similar? Well, the most similar would be my answer. You can see there, it's pretty easy to tell that the one that has the closest slopes to each other is going to be the last one, the one that's second order. Does anybody have any questions about this? This is how you determine whether it's 0 first or second order. Any questions?
No.
Okay. Determining the value of K is pretty easy because you've already calculated the slopes, and it doesn't really matter which of these values you use, or you use a combination or an average or whatever. And again, I've put tolerance on these problems to account for all of this. So in this instance, I think all the student has done is just come up with the slope value here, which is what they really needed to do actually. And you can see that in the equation that we're given for the second order here, the slope is K. So that is K. So when you find the slope, you found K. Now in these other two, you'll get negative slopes, and that's apparent here. See, these slope negatively. So if you did have a straight line on these, it would be a straight line that looks like this and looks like this, but it would be a negative slope. And that would mean that K would end up being positive because the slope is negative. The situation looks like this then. If it was, say 0 order, negative K would equal a negative value. And you can see the negatives would cancel out here, and K would equal M. So K is always going to be a positive value, I guess, is what I'm trying to say there. Does anybody have any questions about that? Getting K? Now half-life, again, you've got the half-life equations here, and the half-life is going to vary depending upon which order it is. And the A0 here is the only one you have to be aware of, and A0 in this instance is the concentration at time equals 0. So that's how you find that. It's a constant value, of course, which is why it ends up appearing in the y-intercept as a constant value. Yeah, so A0 is the concentration at time equals 0. Any questions? Okay, so looking on at the, sorry, go on. Was that a question or just a no? I guess it was a no.
No.
All right, so let's look at the kinds of questions you'll see on the test. So it's very similar, actually, the first question to what you saw on the test we just looked at. So the approach you'll take to this is that you will have A, and you'll have natural log of A, and you'll have 1 over A, and you'll extend out the table just like this student did here on this one, exactly the same way. Then you'll compare slopes, just like we talked about, and then you'll be able to determine whether it's 0, first or second order. Any questions about number 5? Again, you'll know to do natural log of A and 1 over A because of what you're seeing here in this table. You're given A, ln of A, 1 over A. Okay, question 6. What I'm doing here is I'm giving you partial data tables and giving you a bit of, well, it's just really simplifying the information, but looking at this, it can be hard to see how it relates to what we just talked about. So this is a partial data table that's from a reaction that is found to be 0 order, and that's important. It's 0 order. What's the value of K? So for something like number 6, because you've got K and A there, it's really just going to be the slope, and the slope is going to be change in Y over change in X. And 0 order means that the Y is essentially A, and that's the Y axis. Now, how do I know that? Well, I know that because of the table up here, see? So Y, for 0 order, Y is A, right? That's what I want you to focus on. So for something like this, it's not going to be that difficult then. It's just going to be 7.92 minus 3.63 divided by the change in X, which is going to be 52 minus 101. Now I can switch those around as well. Oops, sorry. I can switch those around as well. I could make it 3.63 minus 7.92 over 101 minus 52. It's still going to give me the same result. That's going to be the M value, which is going to be negative, by the way. It's going to be a negative value. And K will end up being positive because M is equal to negative K, which makes the K value positive. Does anybody have any?
That's also from the table.
I'm sorry?
The negative K is also from the table above.
Sure is. Let me show you here.
Mm-hmm.
Do you see here in the line equations? That's the slope there.
Mm-hmm.
Negative K, and
Okay.
positive K.
Okay.
Yeah, so there's nothing even to write down for that. I mean, it's all there given to you. It's amazing, actually, how much information you can pull from this table for this problem. So for this one, for number 7, it's a little bit different. Now, for this one, you're told that it's first order. So that means that Y is equal to the Y axis is equal to natural log of A. And we know that again from the table because first order, you can see that Y is going to be natural log of A, which means there's a little bit of a wrinkle here for this one. It's kind of what we just did, but just on a smaller scale. So we've got 10 and 102 on the time in seconds. And then we've got 4.79 and 3.66 for A. And what we're going to do is just find the natural log of A of each of those. So plug those into the calculator and come up with those values. And those become the delta Y over delta X. And that'll lead to a slope. And then again, that slope will be M equals negative K. It'll come out to a negative value. And you'll be able to then come up with K as being positive. Any questions about this? Is that all right? Anybody have any
No.
questions?
Mm.
Okay. So for number 8, the partial data table of reaction of second order. So the y-axis here for number 8 is going to be 1 over A. And again, we know that from the table. There it is there, 1 over A is the y value. Remember, this is y equals mx plus b. These are y values here. So the y value is 1 over A. So you can see there that all I would have to do is I'd have a 62, 101 for the times. Then I have A, which is going to be a 7.53 and 1.11. Then I'll just do 1 over A, and those become my y values. So it'd be 1 over 7.53 in the calculator, 1 over 1.11. And then use those as the y values. And in this case, m equals k, so that one's fairly simple. It is just what it is. And we know that, again, from the table, m is equal to positive k, because it's going to be a positive slope anyway. Anybody got any questions about that? So it's not that bad. I know that the wording is awful, but you can see why I've done it the way I've done it. It's to give you experience with all the different kinds of orders and how you would get the slopes if you happen to have that particular kind of data.
And when we're taking the test, we can have 1 page of handwritten notes. So if
That's
we want
correct.
to handwrite that table so that we don't have to keep rolling up and down, we're able to do that?
If you wanted to. I think it'd be a waste of time, to be honest,
Okay.
really, because all you're really after there is what the y values look like and what the k
Right.
values are and their signs.
Right. But if we wanted to waste our time in such a way, we could.
Yeah, you could if you wanted to. I'm not going to stop you.
Okay.
Have at it.
Sometimes the rolling and scrolling and all the numbers and the boxes, it gets a little overwhelming. So
I get that. I get that. Okay. Question 9. We've got the partial data table, 0 order. What's the half-life? And you would apply the, I suppose, you would have to scroll back up and get the half-life equation here. So what you would have to do is the same thing as what we did previously. You'd have to calculate the k values in each of these instances so that you could do the half-life equations. And it would just be a repeat of what we just did to get the k values and then applying them to the equations that you're given for the half-life. I'm not going to go through that again. So that would be for questions 9, 10, and 11. Does anybody have any questions about that?
No.
Same kind of deal, really. Oh, the units. Let me talk about the units on each of those. The units on, yeah, that's something I did skip over here. All right, so let's go back to question. I thought the units were in a separate problem, but they're not. They're in the same problem here. So let me go through the units for 0, first and second order. And yeah, Rebecca, was that you who was? I can't see the names here. So was that you who was talking about the slopes and stuff? I mean, the copying out the table. Yeah.
Yes. Mm-hmm.
All right. So this is actually something you might want to write down. You can on your sheet of paper. I think I would do this. And these are the different possibilities you can have. Just for kicks, I'll do time in seconds on each one. And 1 over A and time in seconds. So this is just for the units that I'm talking about here. So this is 0, first, and then second order. And I'm going to make each of them a straight line as they'd appear if they were it. So if you wanted to find the slope of a 0 order and you're just looking at the units on the slope, then it would be m divided by S. Remember, it's change in Y over change in X. So the unit here is going to be M, and the X unit is going to be S. So the unit on a 0 order is going to be molar per second. For log of A, there is no unit because it's a natural log. So the slope is going to be 1 over S. So it's kind of like the unit's 1. It doesn't have a unit. And the S is going to be the delta X. So that'll be 1 over S for the first order. And then for the second order, it'll be 1 over MS, because it's 1 over M over S, which is 1 over MS. So that'd be the unit there. So that's what I'm expecting to see on the units on each of those. So I told you how to get the numerical value. This is how you get the units on each.
And for the first and second order, can we also do like S to the -1 and M to the -1, S to the -1 for the second one?
On the way I'd like you to express it, so that it actually comes out correctly. If it doesn't, you can always email me. But I'll say on what I'm looking for, and you'll see this when you look at the answers. It's M/S, 1 over S, and 1 over MS. That's what you should write down in the units. Make sure you get them. Okay. Make sure you get them correct. Now, if you happen,
it says not to use exponents in the units. I guess that's a parameter of grading, like in the questions on the test. So we have to do the 1 over.
Right. But if you happen to do S to the -1 and you got it wrong, then you would email me and say, well, look, I did get this right. And then I would correct it. I'd be fine with that. But I'm just saying that to follow the instructions, it just makes it easier if you use those expressions as I have them there.
Understood.
Okay. Any other questions?
Are the units case sensitive?
Yeah, are they case sensitive? I actually haven't set them up that way, but they should be, because it should be a big M and a small s, because M is molarity. And I actually have made it clear here what the M is. It's a big M. So yeah, I treat them as being case sensitive. Have I actually made them case sensitive? I don't remember. But if I did, I'd be well within my rights to do so. Any other questions? All right, so that pretty much covers questions 1 and 2 on the paper test. I'm going to move up to question 5 now, which has to do with the rate orders and those kinds of things. This is probably one of the harder things on the test to do. I'm going to give you all a little bit of background here. Let me see how many people we have here. We've got 9. Okay, it's a good number. So what I'm going to do is I'm going to go over the question on the paper test here, and I'll show it without the answer first. Here we go. So the question we're talking about is this one here. And I'll give you a little bit of background as I go through this. And for this one, we're given the reaction and then we're given a rate equation there. Now the thing is with these reactions, they generally don't go in one step. If this reaction was to go in one step, you can see that I'm actually going to bring this back up over here, and I'll take this over to the answer now that you've seen it. So let's say this was to go in one step. This is what the process would look like, just very simplistically. What we'd be talking about for a one-step process would be the simultaneous collision of one N2H4 and 4 H2O2 molecules. On a probability basis, that's an incredibly unlikely scenario. So it's very unlikely that this happens in one step. So what that means is it's likely to happen in a number of steps, and we're actually going to determine what those steps might look like. And we are given one piece of information to help us with that, and that's the rate equation. So the rate equation here is K N2H4 H2O2, which tells us that the rate is going to be determined by this actual equation, which means that the slow step consists only of these two molecules hitting each other. There are also some other steps that are faster, but because the rate is determined by this equation, it's only going to involve one molecule of each of N2H4 and H2O2. I'd really encourage you to go back and look at the video for this, for the introduction, to get more of a grounding of what I'm talking about. But the point of what I'm trying to get at here is that the rate equation tells you what molecules are involved in the slow step. Does anybody have any questions so far? So the first question is asking, can you say whether the reaction is one step or more than one step, and why? Well, I know it's more than one step because the rate equation doesn't contain all the molecules. If it was one step, let's say it was a one-step process, as I said, involves one N2H4 and 4 H2O2s. So the rate equation would look like this. Rate equals K N2H4 H2O2 to the fourth. That's what it would look like. Now, since it doesn't look like that, then we know it's not one step. We know that there's a step that involves N2H4 and H2O2, but there must be a whole bunch of other steps that involve the other molecules we haven't talked about. The 3 H2O2s, for example, that are in the initial equation. So that's how we know that it's going to be more than one step. Bottom line, not all of these reactants are in the rate equation. That's how we know number one is that. See, not everything in the reaction is in the rate equation. Any questions about number one there? Okay, number two, what would the rate equation be if it was one step? Well, it's just what I showed you. So whatever it was that involved all the molecules, N2H4, and H2O2.
When you put the 4 outside of the brackets, is that indicating a power? Is it a change in the math?
It's a power. Yeah, it's the order with respect to that. So it's what we talked about back in question 1, or in question 2 to a degree. But it gives you an idea of the number of molecules involved. So for one step, it's going to be N2H4 and H2O2 to the fourth. So involving all of the molecules in the actual equation. And you see where the 4 comes from. It comes from the coefficient.
Right.
Okay, any other questions about 1 and 2? Those aren't normally that difficult to come up with. It's the last part, the coming up with the equations. Plausible reaction set. That's the hard part here. All right, so let's go through. We'll go through this one here and how I would do it, and then I'll show you how this applies to what you'll be doing on the test. All right, so here's what we know so far. There's a couple of things that I think you need to be aware of. The first thing is knowing what's in the slow step, and the slow step only contains what's in the rate equation. That's the first thing. So what I mean by that is the slow step can only contain N2H4 and H2O2, one molecule of each. That's what we know so far. The other thing that we have to determine, and this is really the hard part, is to determine whether or not the slow step is the first step or not. This is where things get confusing. We have to really use some powerful logic here to make this kind of determination. So here's what we do. I look at the rate equation, which I know contains everything that's in the slow step, and I ask myself this: N2H4, is that a reactant in the reaction we're given it is? H2O2, is that a reaction Is that a reactant in the reaction we're given? And it is. So what that tells me is that the slow step is the first step. So here's what I come up with for that. Now it gives a product. I don't know what those products are yet, but I'll come up with them in a minute. And I know that that's going to be the first step. And everything has to add up to the reaction we're given. Now, I know a lot of you are looking at this and you're confused by that first statement that I was making about the slow step being the first step, right? I know that some of you are, yeah, you might be wondering, well, how would you know if it was, say, the second step? Well, let me give you an example. Let's say the rate equation was this. Rate equals K, say, N2H4 and O2. This is what I would know in that case. I'd know if its slow step could only contain two things, N2H4 and O2. And then I'd be asking myself the question, well, N2H4, that's a reactant. O2 is not a reactant. H2O2 is a reactant, but O2 isn't. So I'd be asking myself, well, where the heck did the O2 come from? And it has to come from a previous step. Where did it come from? Probably a molecule of H2O2, if I had to guess. It certainly couldn't have come from the N2H4. So that's an example of what would happen if the slow step was not the first step. And then you would have to figure out, well, where did that come from? All right, does anybody have any questions?
No.
I find that hard to believe that everybody understands that completely. That you're having this epiphany right now and you're saying, oh, yeah. No, I don't think so. If you've got questions, now's a good time to ask them. All right. Okay. Well, I'm going to assume then that you all know exactly what I'm talking about then. All right. I'm going to throw that out because that's not really what we're doing here. So we know that N2H4 and H2O2, that's involved in the slow step. And one of the things I like to do when coming up with equations is, if I can, I like to form these products here, as many products as I can. I can't make 6 H2Os out of that because I don't have enough hydrogens. I think all I have is 6 hydrogens over here. So I certainly couldn't make 6 H2Os. I might be able to make 1 H2O, so it's possible I could do that. But I think what I would do is I could make N2 and O2, so I think I would go ahead and do that. So I'll make N2 and O2. That'll cancel, that'll take account of those. So N2 plus O2, but that's not balanced. So if I do that, I've got N2 plus O2, that takes account of those two there. And then I can see that I've got 6 hydrogens left over. And I can do anything here. It doesn't really matter. I'll do plus 3 H2s just because I think that makes the most sense. The 6H would be fine as well, but I have to balance it. I'll stop here for a second. Does anybody have any questions about where that 3H2 is coming from?
No, but could you do H6?
Yes, absolutely. It doesn't have to be real. It just has to balance.
You just have to keep referring to the final reaction to know what you have to mix together.
That's right. That's right. And when you're forming products in the slow step, always try and form products that you have in the actual reaction, and then just add whatever it is to balance it out at the end.
Okay.
So the next thing we'll do here, since we've already taken that into account, we know that we got 4 H2O2s here. So I know that 3 H2O2s are going to have to go down here because we haven't taken account of those others. And the 3 H2s from up here will go down here. See, what we're saying there is that we're forming the N2 and O2 products. That's fine. But we're also forming 3 H2s, which aren't products. So those must be reacting with the other H2O2s to produce the other product, which is going to be 6 water.
I did have a question here as you're doing this. Are you kind of canceling out in the final what you've already used up?
Yeah, in a way I am. I don't like to actually put lines through it because it does tend to confuse people. They think then if you put a line through it, never existed.
Okay.
I know.
Yeah, that it's gone.
It's gone, but it did exist.
So you checked off the N2 and the O2 because you got those in the
That's
slow
products.
step reaction.
Mm-hmm.
Okay. Okay. And then you're using the leftover 3H2s out of the 6H2O from the bottom. Is that correct or no? Where did the 3H2s come from? You're just using them out of the slow step.
Yeah, that's right. Because anything that doesn't appear as a product must have been used up in the next step.
Okay.
The reason I chose 3 H2O2s is because we have 4 H2O2s as reactants. So those must be reacting with the other 3 H2O2s. So that would be a plausible fast step there. And you can see it does balance out to 6 H2Os, which is what we needed in the end anyway. All right, does anybody have any questions?
Yeah, I noticed one of the rules that you gave was that the equations had to be balanced, but it doesn't seem like at any time in the lectures or even now that you're actually going through and making sure that they are. Do you just kind of presume that they are, or should you be going back and checking?
Well, no, I did. I mean, the reason I chose 3 H2s was to make it balanced. It's because, you know, you've got the N2 and the O2 here. That means there's 6 hydrogens left over. I put them in as 3 H2s, but I could have put them in as 6H if I wanted to.
Okay, so you're sort of balancing as you go by using what's there only.
Yeah, absolutely. Yes, that's exactly what I'm doing. Yeah. All right, any other questions? I'm going to, so sorry, go on.
That 3H2 could have been like a number of possibilities, like 3H2,
Oh, yeah.
6H, or H to the 6.
That's right. Yeah, any of those. You got to remember that whatever I put here ends up getting used up anyway. So it never appears. We never see it in the final product. So it could be anything as long as it balances and then cancels out down here because it's being used up. Is that okay? All right.
Yes.
Okay, I'm going to open up another instance of my courses here. I just want to show you some of the resources I have for this specific problem. I really feel like you should go through these in pretty deep detail, and that's in the rate equations and reactions folder. And we've got a worksheet here that has 10 problems on it with answers. And then we've got this one here, which has another 16 problems, again with answers. So let's go through these just very briefly, and we'll just determine whether the slow step is the first step or not. So this is often a good exercise so that you can see. And I'm going to ask you to chime in here as we go. I'm actually going to start down here at the bottom. Oh no, I'll start at the top. And we'll start here, and we'll go and we'll see if the slow step is the first step or not. So again, what you're looking for is this. You look at the rate equation. This is the slow step. It has FeOC. If there's stuff in here that isn't a reactant, then the slow step is the second step. If everything in the rate equation is in the actual equation here, then the slow step is the first step.
Could you make the text a little bit bigger?
Oh, sure.
Thank you.
Okay. So looking at number 1, slow step, first step, or second step? Just say first step or second step.
First step.
No, it's FeOC is not one of the reactants.
Oh, because you can't combine them. They have to be separate.
That's right. Now,
Okay.
it does beg the question, where did the FeOC come from? Oh, I think it would have come from combining an FeO and a C, right?
Right. Okay.
In a first step,
Mm-hmm.
right? So that makes that
Mhm.
second step.
Second. Okay.
Yeah. All right, what about number 2? Is the slow step the first step or not? First step or second step?
Second.
No, it's the first step because C is a reactant and there's 2 SO2s that are reactants.
So you don't have to use all 5 of the C's?
If you did, it would only be one step, wouldn't it?
Oh.
But you're using both the SO2s, so
I
doesn't
am.
that make-
I am, but they're both there, aren't they? They're both reactants, aren't they? Both those SO2s. So,
No matter the quantity, as long as they're both there.
As long as they're both present, yes.
Okay.
But
so what would
let me go on. Ask your question. That's fine. Sorry.
what would make this the first step compared to like when Rebecca asked if why aren't we using all 5 C's? But because we're using both 2 SO2s.
Right, because if we did, let's say we did that. Let's say the rate equation was this, just for kicks. It was C to the 5th SO2 squared. What that would mean is it's just one step. Everything's happening all at once with no other steps. That's it.
Yeah.
So that would be only a one-step process. This is not a one-step process.
Okay.
Yeah, I'm sorry. We just know that this is the first step because it has the exact molecules in the rate equation, but maybe not in the same quantity.
Right. Well, what I'm saying is that you don't have to, the C doesn't have to come from anywhere and the SO2 doesn't have to come from anywhere. We're actually given those as reactants. We don't have to make them from anything. In the first problem, we actually had to make the FeOC from something, probably from FeO and C.
Okay.
But for the second one, we don't have to make the C from anything. We don't have to make the SO2 from anything. So somebody's got their thing unmuted, so I'm echoing here. All right, does anybody have any questions about that? All right, what about number 3? Is the slow step first step or not?
Yes.
Yeah, because you can, the AG is there, the H2S is there. Remember, if it was AG squared, that means it would be one step. And it isn't. It isn't one step. That's all it means. What about...
In the rate equations, you're never going to have coefficients. Those coefficients always become a power.
Not necessarily.
Well, I mean, if I guess I'm saying if it ended up being a one step and you're using everything and there were coefficients.
Yes, then yeah, that's true. What you're saying is true.
All right, I understand your qualification.
Okay. Number 4, slow step, first step.
Yes.
Yep, because H2 is there, ICL is there. Number 5, slow step, first step.
No.
No, because the I plus has to come from something. Now, if you all had to take a guess, where do you think the I plus comes from? Do you think it comes from the H2 or the I2?
The I2.
Most likely. So the I plus must have been made in a first step from I2.
Yeah. There was a question about that, I think, on one of the practice things, and it was a little confusing. The I plus and the I minus made I2.
Yes.
You almost want to cancel them out.
Yeah, I know you do, but you can't. So what you would do is you'd say, this is a bit of process. You'd say, well, where did the I plus come from? You say I2 produce the I plus. Well, how would you balance that? Well, it would be I plus I minus would balance that.
And we're assuming these are all neutral charges if they don't indicate, like this one has the I plus.
Yeah. Yeah. That's right. What about number 7? Number 7, slow step, first step.
Yes.
Yeah, because the NaOH isn't. Is it? Now you might say, well, what about the HCl? But again, it's just not used in the slow step. It's used in some other step, but the slow step is still the first step because NaOH is a reactant. What about number 8? Slow step's the first step.
No.
No, because CO is not a reactant. What would you make the CO from? Probably from C plus O2, I guess.
Mm-hmm.
Yeah. What about number 9? Slow step, first step.
Yes.
Yep, that's right. Number 10, slow step, first step.
No.
No, that's right. Number 11, slow step, first step.
Yes.
Yep, because NO2 and F2 are both reactants. Number 12, slow step, first step.
No.
No, because the F plus is not a reactant. Number 13, slow step, first step.
Yes.
Yep, because N2O is a reactant. Number 14, slow step, first step.
No.
No, because N2O2 is not a reactant. O2 is, but N2O2 isn't. I guess the N2O2 would probably be made from the NOs, if I had to guess. 2 of them. All right, so there you go. I mean, that gives you an idea. And that's what I'm trying to get at here. Does anybody have any questions about this? Because it's kind of important that we get through this part of it. Anybody get any questions?
Nope.
Okay, let's go back to the ungraded quiz here. Okay, so question 5, rate equations and mechanisms. That's what we're going to go through here. So the reaction 2A to B has the rate equation blah. What statement is true? Well, let's just, before we go look at the answers, what do you know about the slow step? Is it the first step or the second step?
It's the first step.
Yes, because A is a reactant.
Mm-hmm.
So you'd be looking for an answer there where it says the slow step is the first step. And the slow step is the first step because substances in the rate equation are in the reaction. So you'd find that one somewhere. And you know the thing is, I'm not hiding any of this. You could write this down on your sheet of paper. You know, you just say, which one am I going to look for? Yeah. Right?
Is there a difference between saying that the substances in the reaction are in the rate equation, or the substances in the rate equation are in the reaction? Does that?
It does matter. It does matter because one of them, remember what I was talking about with the. Remember what I was talking about with the being able to determine whether it was one step or not?
Mm-hmm.
If it was one step, the rate equation would be rate equals Ka squared, in which case the rate equation would contain all of the substances from the reaction, right? That's to make that determination. But if you're determining whether the slow step is the first step or not, you're doing it the other way around. It's a case of, all poodles are dogs, but not all dogs are poodles.
Okay.
It's that kind of logic.
Yeah. Mm-hmm.
That's why it matters what the order is.
Okay. So.
All right. Is that clear on everybody for number 19?
Yeah, that's clear.
Now, keep in mind for number 19, it may not be a case where the slow step is the first step. This one happens to just be that. Let's say it was rate equals Ka plus, but then it wouldn't be, and then you'd have to choose a different answer. But you'll see that as you go through and you do the different attempts, you'll get different possibilities for that, for number 19. All right, any other questions? Okay, number 20. A reaction A, B gives C, has the rate equation blah, blah, blah. What are the species in the slow step? Well, the species in the slow step are always just going to be whatever's in the rate equation. It's a pretty simple problem. So this one, the way I'd put it would be this, the way it would work out. A plus B minus. That's what you'd have to put in as your answer. Any questions about number 20? So whatever's in that rate equation, that's the only thing that goes in there as reactants in the slow step.
Okay, so the second plus sign is just showing the relationship between the A and B in the rate equation.
Well, because if you were expressing them as reactants in a reaction, there'd be a plus sign between them.
Got it. Okay.
That's all that's showing. And I do give you an example there. See where it says 2Na plus Cl minus will be written as 2Na plus Cl minus.
Mm-hmm.
And that first plus is for the Na. The second plus is the plus that goes between them in the reaction.
But mathematically, when we're working those out, we would multiply the A plus, like if we were solving for K or
sure,
just a different equation.
Sure, but see what we're doing here is we're taking advantage of the orders and asking ourselves, well, what do the orders tell us about what's going on as reactants in the slow step?
Okay.
And that's the overall application of those orders that we got in questions 1 and 2. It tells you how many are involved, molecules are involved in the slow step. It's very powerful information. But mathematically speaking, you're right. If we were looking for K, we'd be multiplying, yeah.
Okay.
Okay, question 21. Oh, sorry, question 20. Any other questions about question 20? Okay, question 21. So this is something that I see a lot of students really have struggles with, is the balancing of these kinds of reactions. That's why I think doing these problems again and again, it can be very helpful. Oops, sorry. So we've got A3, B3C gives A3B C minus plus something. So we've got to figure out what that something is. So the things I would do here is, first of all, I'd look at it and I'd say, well, is this balanced for atoms, for example? And I see it isn't. We seem to be missing 2 B molecules. Everybody okay with that?
Yes.
Yeah.
Is that a no? Was that a no? Somebody's not okay with that? No? Okay. So we've got B2. But not only do we have to balance this for atoms, we also have to balance it for charge. And you can see that everything on the left side is neutral, but we have a minus on the right side. So I have to put a plus on here to balance that out.
Mm.
So it'd be B2 plus would be the answer there.
If the C on the left, on the reactant side,
Let's do. I'm going to preempt you.
okay, you're gonna play around with it.
This is the kind of question you're asking, right?
Yes, that's exactly right. I wanted to play around with that and see the change.
Okay. All right. So I want everybody to look at this, and Rebecca, I want you to zip your mouth for a second, so that we can. I'll get an answer from somebody else, because I think you know the answer. So I'm going to ask you. So anybody else want to come up with what would be required to balance that out? I'm looking for an answer from anybody here. Anybody willing to have a go? Plus what?
B2 minus?
Yep, B2 minus. And how do we get that? Well, we got the B2, that's okay. The minus though, see this is minus and minus will give 2 minus. So we had to put a charge on this that would allow it to add up to whatever was on this side. Okay, so Rebecca, since you asked about it, I'm going to ask you, is that okay?
It is. It's a little confusing with the C2 minus. For a second, I was thinking there needed to be 2 C's. I do see that the B2 minus because it's not 2 C's, it's 2 negative.
Right. Now remember that if it's a superscript, it's always a charge.
Mm-hmm. Mm-hmm. Yep.
Okay. So the other one, we got A3, B3, C. Let's make it plus just for kicks. And A3, BC minus. Ooh. Okay. All right. So any thoughts about that? About what we'd have to do to balance that one out?
B2 plus 2.
Yeah, it'd be B2 and then 2 plus or plus 2. Yeah. And I'd hope that I would have both of those answers in there if I had something like that. But yeah, so minus and 2 plus would add up to plus. See, the minus and this would add up to this. So that's what you're doing. You're effectively trying to figure out, well, what charge do I have to have there to make them balance out so that we have the equal number of charges on each side of the reaction. Okay, any questions? Any questions? Okay. So remember what you can do here is you can take this ungraded practice test as often as you want. You could just practice question 21 on its own as many times as you needed to in order to make sure you're understanding the pattern there and figuring out how to get the charge, especially on that second species.
As we take the ungraded test, does
Yes.
it generate different numbers, different combinations, or is it always the same?
So it's always different. Otherwise, there wouldn't be any point.
Okay, excellent. Good.
No, that's what makes it an excellent tool to study with. But you know, it's more than just understanding how to do the practice test of the ungraded copy. I think having some background by watching the videos and having some context is really important as well. Not just being able to do the problems, but knowing the background behind them so that you can do any of the problems as they appear.
That's true. I've watched all of the mini lectures, but I'm actually overwhelmed on where to start practicing because it looks like bajillions of hours of practice opportunities on the, I mean, you have plenty there, but this seems like it would be a more focused use of what the lectures and the explanations were about. And then if I needed more, I could maybe go into like the little links for each question, that type of thing.
Yeah, sure. Well, you know, if it was me, what I'd do is I would do the extra credit, you know, those practice tests and things as I completed each part of it to make sure I understood what I was doing there. And then I would do each of these questions as I'm doing them here in the ungraded copy, making sure I can do each one individually.
Okay.
Yeah, so it's not too bad. I think that's how I'd focus.
Okay.
And if I was having problems with one specific problem, I just do that problem multiple times.
Right. Okay.
All right. Any other questions? All right. Question 22. This is the nasty one, as you can see here. So I give you an overall reaction and I give you a rate equation. And then, oh gosh, look at that. Ooh, good luck guessing. I think you're going to have to know how to do it. All right, so let's go through and we'll do this specific example here, the number 22. All right, so let's look at this. Oh, slow step, first step or not? Slow step, first step.
Not.
Right, why not?
It only has part of a molecule, so it must have come from somewhere.
All right, so if you had to guess where the A2 came from, where might you think it came from?
Sure, the A2B.
That would be my guess too. That's what I would choose too. All right. Well, that's good. See, that's nice logic right there. And now I'm going to stop here for a second. Does anybody in the audience have any questions about what we just talked about just now? It's really important.
So
Because that-
KA2 is not the first step, because you can make the argument that it comes from the reactant A2B.
That's the whole point though, isn't it? It has to be made from the A2B in some other earlier step.
So if it was a slow step, it would have been just A2B instead of just A2.
Exactly. If the slow step was the first step, yes, absolutely. You know, and what you just talked about is really key, because that's a big reason that people end up being confused. So I'm really glad you brought that up. All right, so this is the information we have so far. So A2 gives something, and we know that that's a slow step. We also know that there's a step up here that has to be put in too, and that's where the A2 came from, but I'll get to that in a minute. There may be a third step, or there may not be. We'll see. We'll see. I don't know. We don't know until we try this to see. AB plus C plus A2. Okay. So what I'll do is I'll say, well, okay, so if the A2 is not, if this A2 is not in the first step, it must have come from somewhere, and we posited that it came from the A2B. And if I was doing that, it'd be A2 plus B. This will be fast. So any step that isn't slow, obviously, will be faster. Okay, so I'll stop there for a second. Does anybody have any questions about why I did what I just did there? See, I knew that the A2 was in the slow step, and that the slow step wasn't the first step. And then I came up with something where I said, well, the A2 has to come from somewhere. So the A2, go on.
No, go ahead.
So the A2 came from the A2B.
So would you go down below and check off the A2B as being used on the reactant side of the final?
You could. Yeah, we can do that.
Okay.
But we can also check off the A2 down here as well.
Because we produced it.
Yeah, we've produced it already.
And so we would leave that alone. Well, no, we're not going to.
So the next thing we'll do is we'll say A2 gives, well, 2A. Now, I know some of you looking at it and say, well, isn't that the same thing? No, let's have a look. If you had Cl, for example, Cl2, Cl2 looks like this. If you had two Cls, that's two separate Cl atoms. So we can do that. So A2 going to 2A is actually going to be something we can do. It's the only thing we can really do there. So then we know that 2A is not a product, so we know it has to come down here. Now, what haven't we taken into account here? Well, we haven't taken into account this AC down the bottom. So this AC here, so we know it has to add to that. And if we did that, then the products here, we got A2B, A2 plus B here.
What happens to the B in the fast step?
Yeah, that's a good question. It comes down here, I'm sorry. It comes down here as well. I was wondering where it went. Yeah, it has to come down here. You'll notice that B is not a product here, so B has to come down here as well. And that will help us get what we need to get. This will give us the AB plus the C, right? Oh, hang on. Make sure I'm getting this right here. I think I've messed something up here. AB It's a bit embarrassing, isn't it? I can't. I seem to have messed something up here. AB.
Well, wouldn't you still finally have one more product in the third step? You'd have the A2. You'd have to combine the leftover two A's there.
Oh yeah,
You have to get it back.
You're right. You're right. You do have to get it back. You're right.
Because we used it up, and that was concerning because I knew we needed it.
Yep. Yeah, you're right. So yeah, that's exactly how it would work. So it actually does work out fine in the end. Usually that confused me for a second. But yeah, you're exactly right. We used it here so we can form it again down here. That's exactly right.
Well, and we have to because we need it.
Yeah, we need it.
It went away.
It went away, so we have to get it back. You're exactly right.
Okay.
So then what you would do is you'd have to hunt through all these to find the reactions that match that. It does look though like it's the first one, doesn't it?
I thought that.
Yeah. Yeah. It's not always going to be the first one, but it happens to be the first one for this one.
With one like this that has quite a few A's and B's and C's, would it be helpful at all to just to double check yourself, to go through the sets of reactions above and sort of cancel out?
Oh yeah, absolutely.
Used used.
Absolutely. See, that's what confused me initially. I was saying, oh, hang on, where did A2 go? Well, it got used up, and then it got reformed in that one step. Yeah.
Interesting.
Yeah. No, that is interesting. It is interesting. Anyway, so that's an example of how you could do that one. Okay, I'll do another one here. Then I'm going to look to finish in about 10 minutes or so. Give me a little bit of a break before we get on to the lab stuff. All right, so I will exit the preview here and we'll re-roll. And hopefully we can come up with something different. And you'll see that, yeah, we should come up with something different here. But I have a lot in each pool, so it's going to randomly pick. I'll be pretty embarrassed if it comes up with something the same, but there you go. All right, no, I like this. Okay, slow step, first step.
Yes.
Yeah, because AC is a reactant. So I know it goes like AC gives something, and that's going to be slow. And then this is all going to have to add up to A3B plus AC gives A2B plus C plus A2. Okay. So looking at that, I could form C and A. C is one of the products here. I can go A plus C. That's what I would do first for the slow step. And my logic there being that accounts for one of my products. And then down here, I know I'm going to have A, and we're going to have to react it with A3B. And lo and behold, that would give us A2B plus A2. That would work, and that'd be fast. So that would allow us to get those other two products. So that one's not too bad. Any questions?
No, that one was pretty straightforward.
Yeah. So it shouldn't be too hard to find the reaction that goes along with that. Make sure you get the slow and fast steps right, though. Looks to me to be the third one down. Yeah. All right. Any other questions about that one? Okay. let's re-roll. So you see this approach that I'm using here is one you can use, obviously. You can take it unlimited times, so you can practice that way. All right. Slow step, first step. Oops, sorry. Wrong one. Oops. Didn't mean to do that. Sorry.
I would say yes.
Yes,
The first step.
it is because A3B is a reactant. Don't take any notice of the fact that I've selected this option. I didn't mean to. In fact, I'll go down here and select some other option. Okay, so we know that it goes A3B, and that's going to be the first step, and it's going to be slow. And then we have to have them all add up to A3B plus AC gives A2B plus C plus 2. So a lot of them are fairly similar in nature here. And that can make them confusing when you're going through them, I guess. Now, what I would do, I would make one of these. I think I'd probably make the A2B product.
Mm-hmm.
And if I did that, that would require a plus A here to balance it. And then the A would come down here, and we still haven't accounted for that. So A plus AC would happen to give A2 plus C. And that would be fast. Any questions? Now, the reason I'm coming up with those products is because I need them. I just want you all to understand that. I'm not just pulling them out of thin air. I need them as products in my final reaction. So that's why I come up with them. But it does happen to balance out that way. It's not really a magic or anything. All right, any questions? All right, let's re-roll. We'll do one more. One more. Oh yeah, I like this one. I like this one. Okay, slow step, first step.
No.
No, why is that?
Because it's not in the reactant.
Yeah, yeah, that's right. The A2C is not a reactant, is it? All right, so it must be the second step. So that begs the question, doesn't it? Well, where the heck did it come from? Well, it would have to be made from A2B and AC, wouldn't it? You can't just make it from AC. But if I did that, it'd be A2C plus what?
Plus B.
Plus B. Yep, that's right.
Wouldn't there be an extra A?
Would there be an extra A? Yeah, so it would be AB, right? Yeah, you're right. So it'd be AB. You're right. That's correct. All right, so let's look at, this all has to add up to the final reaction.
When it's not the first step, do we assume it's the second step? Is it possible it could be the third?
I suppose it could be, but I think if you're just looking for a plausible reaction set, you can assume it's the second.
Okay. This is one of many scenarios, so we can
absolutely,
plug that in as that. Okay.
Okay, well, AB actually happens to be a product as well, which is cool. That helps. And you can see here, if we do A2C, we can actually split that into C plus A2. and we're done. There is no need for a third step in this case, because we can actually make that from the first step. Sorry, from the second step. That would be it. So any questions about that one? All right. Well, we'll leave it there for today then, folks. If you all have any questions, let me know, and we'll we'll go from there. Okay. Anyway, thanks for all coming today, and I'll see you all. Well, see some of you in a little bit.
All right. Thank you.
Thank you. Bye-bye.
Bye.